Some of you have kind of heard about the origin story of Earth Engine, why we started all this. But the gist of it is there's a lot of incredible satellite data, environmental data, aerial data, ground-based data that has been collected over decades. A lot of it is free, open, public data. Like, for example, the NASA satellite missions like Landsat. Europe, with the Copernicus mission, the Sentinel satellites, they have put together, I think it's the most ambitious constellation or configuration of satellites to cover land, ocean, atmosphere, going out to 2030. They've made a real commitment on this with A and B versions of each satellite, so people can really count on this data, and it's beautiful data. But what happens to this data? Typically, it comes off these satellites and it goes into tapes, into government archives that are really well locked and secured. So the data is very safe, but historically it hasn't been that accessible. For example, the Landsat data comes off the satellites and goes onto tapes in a vault in South Dakota. And this is really where we got started, because scientists came to us and said, there's 30 years, 35 years of incredible historical data on those Landsat tapes that no one has ever really had a chance to completely, thoroughly mine. You can get a few scenes, but you can't get all of it because you have to put in a request and so on and so on. So that was the idea. And actually, I didn't put in a slide on this, but the real instigator was scientists in the Brazilian Amazon who said, we're losing 1 million acres a year of forest to tropical deforestation. It's happening in remote parts of the forest that are not well monitored. But with daily satellite imagery, you could create a virtual monitoring system. But the problem is it's like terabytes or petabytes of data. And it takes weeks to run the analysis on a single computer to do that change detection. And by the time they would get the result, eureka, it's irrelevant. It's way too late. And they said, Google, you brag about having a lot of computers. You have the satellite imagery data in Google Earth and Maps, but why not let us have access to it for science, for analysis, for change detection, for monitoring and measuring a changing planet, not just looking at pretty pictures of it in Google Earth and Maps. So be careful what you challenge us to do, because if it's hard enough and important enough, you may convince us to do it. So we worked with Aeros Data Center and now more recently with European Commission to get all this incredible data off tapes and into Google data centers, where the data is stored, co-located with massive amounts of computing for deriving insights from the data. And as many of you know, so many of you are remote sensing people, imagery is hard to work with. On the left, as Landsat 7 SLC lines that are gaps in the data. On the right is clouds. Much imagery of the world is cloudy. But because these satellites are historically collecting many images throughout the year over the same place, you can get a couple dozen, for example, Landsat pixels. If you stack them all up and choose the best one, you can basically composite a cloud-free mosaic. And this is a very simple thing to do when you have a lot of computers and you have all the data. But it's a surprisingly important thing and difficult thing for many people who they just need a cloud-free image. And it takes way too much work for them just even to get to that starting point of their algorithm. So once we developed not just having all the data, but developing some basic infrastructure for storing the data in an analysis-ready form so it could be operated on in parallel, and that we had algorithms to do geoprocessing, we turned our attention to our own base map and created this 15-meter cloud-free imagery of the Earth based on Landsat and more recently Sentinel data. And that's the base map for Google Earth and Maps. You can zoom all the way in to, I think it's 10 meters per pixel actually. with the Sentinel data. But what did that take? Well, it was, a lot of CPU core hours. It would have taken 14 years on a single computer to do that. But because we ran it on, I think it was probably 10,000 computers in parallel, we can generate something like that in a couple of days. That's when my boss first said, maybe there is something to this Google Earth engine. And similarly, now that we had all of the Landsat data going back to the 70s, we then stitched together, and Chris Herwig is our lead on this. I'm not sure if he's in the room. I think he is. If you want to learn more about this, find him during office hours. But creating a cloud-free global image Landsat resolution for every year from 1984 to 2016, so 32 of those, and then stitching that together into a browsable, zoomable time-lapse animation of the entire planet. And you can find that on earthengine.google.com/timelapse. This is Las Vegas growing while Lake Mead is shrinking. Again, this took 3 days of processing. I think we figured out this would have been something like 300 years on a single computer. So one of the kind of the secret sauce of Earth Engine is it's really just kind of that we've collated and curated hundreds of data sets that you have all been asking for, starting with Landsat and Sentinel and digital elevation models and weather data and all these data sets that you need for your methodologies, for your algorithms. We have all these feeds now that are automatically running. We now have more than 11 million images in our data store. We get 6,000 new ones every day. Think about it, all the Landsats, all the Sentinels. That's a lot of imagery. We have more than 8 petabytes that, again, is staged for parallel analysis. So there's this massive database, and then lots of computing, and then we've put together a web interactive development environment. And this turns out to be really important because you don't have to download and install software. You just point your web browser at the cloud, and all the data is there for you, all the algorithms are there, the functions are there, with a scripting environment, JavaScript, and you can also use Python, that makes it very easy to develop algorithms and run them and share them. You're going to learn more about all of this, so I'm just kind of, and for some of you, you've been working in the code editor, you know this very well. For others of you, you're going to be learning this this week. So the insight that this platform represents is the old model was, okay, I want to do some remote sensing. I need to go find all the data, download all the data, find all the algorithms, all the software I need, install that on my computer or my computer cluster, keep that all running, and then finally get to do the good stuff, right? And Jim Gray, the late Jim Gray of Microsoft said, it can be more efficient to move the questions to the data rather than the other way around. And that's this new paradigm. So that's Earth Engine, Google Earth Engine. We call it Earth Engine because it's an analytical engine for the planet. It's an environmental engine. That's one way to think about it. I thought I'd share with you something about you, which is we're seeing a lot of growth. These two charts are showing on the left. In blue is people who have signed up for Earth Engine, going back to, I think it's 2013. The red on the left is people who've signed up for the dev list. So I think we need to do a better job getting people on the developer list, is one conclusion. And then the right is what people are actually doing stuff. So in a way, that's maybe the most important. The blue bars are sessions in the code editor, and the red is people that are active in the previous 30-day period. So we're now up to about 45,000 users, of which in any given month there are about 10,000 people in the code editor. And the funny thing is, when we were first inventing, hey Tasso. When we were first inventing Google Earth, I think it was Matt Hancher who said, there's probably 10,000 people on the entire planet who will be able to use this. Because it's like so niche, right? It's such a niche tool. So I'm hoping we're going to really prove him wrong, and we're going to keep growing. But yeah, it's all about, you know, the community. There have been now hundreds of peer-reviewed scientific publications that the community, you guys have written, that were powered in some way by Earth Engine in the most prestigious, high-impact journals in the world. That's been so inspiring for us to see. Science, Nature, you know, remote sensing of the environment, and it's accelerating. I want to have a graph of that, but we don't even know all of them. If you go into Google Scholar, it says something like over 1,000, but anyway, this is really exciting to us. Many of you know the Hanson paper, but I like to mention it because it's kind of the stake in the ground. It's the foundation. It was the first big science result done on Earth Engine. Matt Hanson was, I consider him brave, because this was 2012 when he started working on Earth Engine. And I think a lot of the scientific community was sort of skeptical. What is this thing? Is it a toy? Is Google serious? Is it really going anywhere? Does it work? And he came and he met with us, and he said, oh, let me just try doing a water mask for the Congo. And in a few lines of code, his thing was running. He had the result. And he said, OK, let's scale it up now. Let's try to do the whole world. And it's a remarkable result, which was the first high-resolution map of forest loss and gain and extent from 2000 to 2012, and it's been updated every year. It was published in Science in 2013. I just checked, it's got almost 2,000 citations. That's 100 more than a month ago. It's really having an impact. And one of the reasons is the output of this was not just a paper, but it was all of those data sets were published, made as open data, Creative Commons attribution, do whatever you want. And there was this interactive site for browsing the data. We have the data available on Earth Engine. So we did everything we could to make it accessible for derivative scientific products. And this is an example of one we're excited about. Anoop Joshi and his team working with the WRI Global Forest Watch people and a bunch of other folks took a look at where native forest habitat required by wild tiger populations, where that still existed, and determined that if those areas were simply protected, and no further, simply is not the right word. It's hard, we know, to protect intact native forest. But if those were protected, native wild tiger populations could double by 2022. So that was a hopeful finding. And again, he wrote about how it wouldn't have been possible to do this global study without the availability of these tools and data. One thing I like to really emphasize is we are not the scientists. We are not. If you come up to one of us and say, oh, I don't agree with so-and-so's algorithm running in Earth Engine, we're like, talk to them, because we're providing the infrastructure. We're not the ones providing the scientific methodology, generally speaking. And so here's a different forest analysis that was done by UNFAO, which just got front cover of Science last month. And their study was on dryland forest. And they discovered sort of previously unmapped forest biomass that added 9% biomass to the world's accepted biomass. So that was kind of good. Switching to a different natural resource, water. The European Commission Joint Research Center. This study took more than 2 years. I think of it as the global surface water analog to Hanson, where they, over a 32-year period, analyzed at 30-meter resolution the existence, the occurrence, and change in surface water. So for every pixel, has it always been water over 32 years? And every observation, has it never been water? Or is it seasonally water, and so on? This turns out to be quite important. I think we're looking here at the Brahmaputra. And they created a site, globalsurfacewater.appspot.com, where you can, just like Hanson has a site, where you can interact with the data, you can derive statistics for every pixel, you can download the data, and so on. This was, actually I heard that it was 10 million hours of computation. This was the biggest analysis done to date in Earth Engine. And our friends at the European Commission calculated that if you wanted to run this on a single computer, it would have taken 1,212 years. You would have had to start in the time of Charlemagne and hope that you could keep your computer running, and then you would have your result by now. So I want to switch gears now to some of the applications, because there's the science, but one of the things we don't want it to stop at the science, right? We want to facilitate by having all the data, the algorithms, the methodology, everything in the cloud. It should be easier, and it is turning out to be easier for algorithms to become operational, to be put into practice, to be put in the hands of government agencies, NGOs, people on the ground. So it doesn't just end with the paper. So I want to talk about just a couple of those applications. This is one, I believe it's the US Department of Agriculture, massive mining. I think it's 1 million acres in the American West, trying to determine, looking at tree canopy, where there is good or not good habitat for sage grouse. I think I have 3 other examples where I'm focusing here on a specific thing that has caught our attention, which is we're hearing that Earth Engine is it's facilitating remote sensing practice and science in parts of the world that have historically struggled with that. So for example, Southeast Asia, Vietnam, Thailand, and so on, Indonesia, because they have issues with bandwidth, they don't have access to computing, and so on and so on. So there's been a fantastic project I think you're going to hear more about, so I won't spend that much time on it, but USAID working with NASA in the Severe Initiative to do training and development, capacity development in this region based on Earth Engine. And what I personally like to see is they do a lot of outreach to women scientists, and often they have almost as many women involved in these trainings as men. Yes. Another example in the developing world, government of Australia has flown high-resolution LiDAR, 1-meter LiDAR, not only for their own coast, but for various South Pacific islands that are under threat of coastal inundation due to sea level rise. And many of those countries have not had the data or the capacity to plan for eventual changes. For example, Vanuatu, Tonga, and so on. So they've created a tool powered by Earth Engine. We're looking at a part of Vanuatu here. Now, this is showing a typical inundation at high tide today. And now this is showing inundation in the year 2100, according to conservative estimates of what the sea level rise will be. And then further, because we also have high-resolution imagery, they could count and identify the buildings that will be at risk. And so now the government of Vanuatu is using this to plan the relocation of certain of their buildings. This won a United Nations UNFCCC Lighthouse Award. There's a group at Desert Research Institute and University of Idaho that has pulled together many, many data sets, again, powered by Earth Engine, to look for anomalous wetness, dryness, temperature, and so on. They've put this all together in something they call Climate Engine. And a very important use case is for famine early warning, FuseNet, if any of you have heard of that system, to try to give more advanced warning to smallholder farmers in Africa, for example. Historically, the data that they've been able to use has been MODIS scale, so it's been very coarse resolution. Now they can do it, in near real time on Landsat resolution, and it makes the results much more relevant. The last example is It's called DISARM, Disease Surveillance and Risk Monitoring. The idea here is for the government of Swaziland. They're trying to eradicate malaria in the country. They're down to a small number of percentage, but getting that last bit is very difficult. The map on the left in red is their current best guess of where there is risk of malaria. It's half the country, and it's not that actionable. On the right is a near real-time update of where there is actually risk based on looking at temperature, rainfall, greening of the landscape, proximity to villages, and so on. Now, these kind of algorithms have existed before, but what is being transformative in this case is because all of this data, all the weather data, all the imagery is coming in every day to Earth Engine, then the algorithm can be running automatically every day, and it can give the information, the sort of spatial decision support to the clinicians in Swaziland in near real time, and they can make more intelligent decisions about where to do bed nets and so on. So that's some context. So where are we now? You're going to learn a bunch of stuff this week. I'm not going to tell you everything you're going to learn. That would take away the fun. But there are a couple areas I wanted to highlight. One is that you saw the growth curve, right? And with that, some of you have felt some pain, right? Like, why is the system slow at such and such a time of day? Or why can't I get the scale that I used to get, or whatever. And we have a lot of computers at Google, but still we have to keep growing and mobilizing in response to your needs. And so we've put a lot of work, and we're going to continue to put a lot of work, and you'll hear more about that, into improving performance, stabilizing performance, getting to the point where one user can't take the whole system down for everybody else, that kind of thing, which has happened, and we're not going to name names.
They're very proud of their accomplishments.
Yes. So that's all I'm going to say about that, but you will hear more. The big thing is vector data tables. So we've felt your pain that we started with a focus on massive image processing because that was an unsolved problem. But guess what? Most real analyses also require some vector data. It's training data, or you're clipping the analysis to the results of the analysis to political boundaries or whatever. And the solution that we've had you guys use with fusion tables, we'll just admit it was not ideal. So a couple things, there's a couple announcements here. One, which some of you may already know, because this happened, I think, 2 months ago, is in addition to having image data sets like Landsat and Sentinel, we launched table data sets, vector table data sets, just the beginning, but like the image ones, you can vote on what additional data sets you would like us to host. So there are things like political boundaries and hydrosheds and ecoregions and so on. But we're just at the beginning of that, so we really would like your input on what else you would like. And for example, if you do a search, you now see tables in addition to seeing rasters. And that I did a search on census, and here is census data that we have, US Census data. This is 20 million road segments. You can go anywhere in the country, and you have access to this data. Now, here's a quiz. Who knows what this data set is? What? Yes. So yeah, the WDPA, the World Database of Protected Areas, it's like the base map for protection, for conservation of the planet. And it's been carefully managed and shepherded by UNEP WCMC for years. I think it's like 193 countries, lots and lots of data. I'm very excited to say that we just, a couple of hours ago, all agreed and signed everything that we can host the WDPA in Earth Engine for you guys to use. Yes. And I wanted to mention Andy Arnell and Samantha Hill from WCMC are here. Yes, okay. So they helped arrange all this, and I think they're going to be doing a session this week, a breakout session. So if you have questions, go to that session. We're very, very excited about this. Okay, so that's hosting public data sets. The other big news is we are now allowing, as of about an hour ago, you to upload your own vector tables natively into Earth Engine. So, yes. So I just did that screenshot about 5 a.m. this morning. You now have table upload. It's live. And just for those of you, I just have to grind in what the pain was. If you had a shapefile, you used to have to convert it to KML and then KML into fusion tables and then reach over into fusion tables from Earth Engine, or use shape to, anyway, it was just not fun. And now there is a direct import. Yes. We apologize it took us so long to get to this, but we've been busy on other things. And another important thing is not just that the workflow is easier, but that the scale is much, much greater. I don't know if it's 10x, but it's for the initial type of data that you can upload is shapefile. We will add others, CSV, NetCDF, whatever, fill in the blank. Basically, I'm hoping anything GDAL can support. Anyway, I don't mean to commit my engineering team. But what you can do right now is shapefile, and so we can handle what shapefiles can handle, which is basically 70 million points. Here is all of the GBIF, Global Biodiversity Information Facility occurrence data. That's about 10 million points. This is data from volunteer ships that are collecting sea surface temperature. That's the color ramp is sea surface temperature from warm to cold. We still have performance tuning to do. Eric wanted me to say that it's going to get faster, but you should be able to directly natively upload shapefiles and do much bigger data, vector data than you could before. All right, almost done. Looking forward a little bit. The future is cloud. Google is heavily building out the Google Cloud Platform suite of tools and data. It's awesome, right? And many of you are using some of those, or you want to use some of those in coordination with Earth Engine. And we haven't always had the best integration points. So this is something we're really focusing on. Matt and some other folks are going to be talking about what we have now, what's coming, so you can begin to get your minds turning on what's going to be getting easier. This is one thing we launched last September. The Landsat and Sentinel-2 data that we're getting into Earth Engine, we're now also storing as GeoTIFFs in Google Cloud Platform Public Data Program. So people who are using Cloud Platform tools like Compute Engine can have free access to the same data. Just quickly flipping through a couple of the integration points that exist now, and this will expand, is what you should be thinking. Many of you, when you're building web applications powered by Earth Engine, you're using App Engine. It's super convenient, and we do have good connection points there. Cloud storage. We have some decent two-way upload, import from cloud storage, export to cloud storage. Let's say you produce a result, you want to generate map tiles or generate a GeoTIFF that you can take somewhere else or do something else with. We've got some decent integration there already. Looking ahead, we want to make it possible from Compute Engine. Let's say you've got some workflow that has nothing to do with geoprocessing, but then you also have some geoprocessing part of it. You should be able to do both from Compute Engine and not have to somehow split up your workflow. There's a set of things here that go through some ideas we have. One of them you're going to hear about this week of integration with Data Lab. Is it Jupyter or Jupyter? Anyway, an IPython notebooks. Tyler's going to talk about that. And another really exciting thing is deep learning. TensorFlow and Cloud ML. There's some very cool integration points coming between the two. And it could really be the next wave of innovation on remote sensing. So you should be thinking about that. So kind of stepping back, you can imagine where we're heading is that Earth Engine itself could become a cloud service, just like BigQuery or Compute Engine or Data Lab, that makes all this very, very seamless. And one other point that I'm hoping Peter will talk about, or Joel, later this week, the terms of use of Earth Engine from the beginning have been non-commercial, right? Science, nonprofits, this sort of thing. And we're getting increasingly people saying, I have a commercial idea, I want to use Earth Engine commercially, and we've kind of said, blah, 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 go away. But they don't go away. They say, we love Earth Engine, we want to use it in this way. And so we realize that, yeah, even with our goal to, we want to change the world, that being able to help people build sustainable businesses on our platform is a good thing. So this is going to be the way we do it. We will always maintain the free, non-commercial use of Earth Engine, what we have today. But there will be, and we already have a pilot version of it, a version that you can use for in a commercial context. And I think Joel will be talking more about that, I'm hoping. So as Thao mentioned, we're really excited. Our Google Earth team, which is like the sister team to Earth Engine, has worked for 2 years to reinvent Google Earth from the ground up. It runs on the web, Chrome initially, and it's eventually going to be cross-browser, I hope later this year. It's on Android, the same application, and it will be coming out on iOS. What's there right now in the first version is very oriented toward consumer-friendly. It's got storytelling. It's got fantastic search. It's got a feature called I'm Feeling Lucky, where you roll the dice. We fly you somewhere interesting and fun to learn about. That's a little off the beaten track, but probably cool. Not like a landfill or something. But where we're going is we're going to make it, many scientists have traditionally used classic Earth with KML for scientific data visualization in 3D. And we intend to support that in the new Google Earth. And it will be even better because you'll be able to share a deep link with a colleague or post in a blog post or whatever. It won't be this, got to email a KML to somebody. It's going to be very nice. So there's no action yet, but it's more like stay tuned that I think for 3D scientific data viz. And we intend to integrate Earth Engine with Earth. So for those of you who are frustrated that you're only looking at it on a Mercator projection, you will have a globe at your disposal. All right. Last point. This came, I think, 10 days ago. We were very pleasantly surprised. The Journal of Remote Sensing has sent out a call for papers. They're dedicating an issue to Google Earth Engine applications, 100% dedicated to Google Earth Engine applications. And the deadline for submission is June 1st, 2018. So your job this week is to learn a lot, write an amazing paper, submit it, get it accepted. Now, this is the first time we've seen this, so we're very excited about this. The other kind of teaser is we expect to be able to give you some interesting news in the next day or so from remote sensing of the environment. And that's all I'll say about that. All right, thanks.